What happens if you combine a resistor and a capacitor in a circuit?
Resistor resists and
Capacitor capacitor.
Yeah. So we have an electromotive force, a resistance, and a capacitance. Believe it or not, if we want to graph the transfer of voltage, charge, and current, it's not actually super simple. It follows an equation called the time constant equation. Looks like this. Similar to like the one in chemistry. If you're doing chemistry, Jacob. So like this is the initial voltage, this is the final voltage, and the same with charge. And then you have current, which looks like this. So we're going to derive how to solve for this time constant equation with math. Take notes on how to do the derivation, so you can remember how to like reproduce it, because you need to do it on the test most likely. And then also like the most important formulas of the derivation. Okay, so we're gonna
wait. No.
Fine. I'm gonna move this off to the side though.
I mean, it's just a battery capacitor.
Yeah.
Wait, so what's the thing that goes down?
That's current.
And the thing that goes up is voltage?
Voltage and charge.
What's the X?
But they're not the same. I mean they're
Is that over time?
This is time, yeah.
Okay.
So let's say we have like a switch.
Yeah.
If the capacitor is empty and you close the switch, it's gonna start filling up the capacitor.
Oh, so that's inside the capacitor?
Yeah.
Okay.
Okay, if I erase the equation now? I mean the graph. Okay. Does anyone know what first equation we should start the derivation with? Any guess?
Ohm's law.
Ohm's law? No.
Yeah. It's like the capacitance law.
Capacitance law.
Kirchoff's first law.
Yeah, Kirchoff's first law is really
Hey!
Woohoo! Sum of delta V equals epsilon. Okay. So we're gonna treat all these as positive because it makes it simpler. So sort of this is gonna be like a voltage drop, and this is gonna be a voltage drop. The capacitor is gonna charge up in the opposite direction as the EMF for it to cancel out. But we're gonna treat all these as positive values in our equation. So that means that epsilon minus voltage of the resistor minus voltage of the capacitors would equal 0. Okay. What is the voltage of the resistor today?
That's just the voltage of the. Wait, let's call that. So it's just the voltage. It's just epsilon,
No.
right?
At any certain time, the voltage drop of the resistor.
Oh, the voltage drop of the resistor.
Yeah.
It wouldn't just be the current times
IR.
Yeah, current times resistance.
And what's the voltage of the capacitor at any time, Russia?
It's a
So
logarithm.
remember
right?
we have capacitor or capacitance is equal to
Q over V.
Q over V.
Or not the square root of time.
Huh? Bro, you're going. No, it's not.
Time.
Or log of time.
It is a log, but there's a bunch of.
So it would be Q over C.
Q over C is the.
Okay.
Cool. Okay.
And I was thinking about that graph and how it like doesn't increase.
Yeah.
Often.
Next step. Can anyone guess what the next step of this is?
DQ over DT for the.
Good job.
Yes.
Epsilon minus dq dt times r minus q over c is equal to 0. Because now we have just q is the thing changing in this equation. we have a dq, dt, and a q.
Mhm.
That's going to turn into a differential equation that we're going to have to solve for.
Wait, what's C again? Current. No, I is current. What's the C?
Capacitance.
Capacitance. Oh.
So
Alright. So next we're going to multiply all by
What
c.
were we trying to find in this question?
We're trying to find an equation for q based on
Oh,
time.
okay.
And then we're going to also find an equation for v based on time and an equation for I based on time. So let's multiply all by c. C epsilon minus dq dt RC minus q. And that just get q by itself here. Okay. And another thing real quick. Let's inspect like the initial and final properties of this this circuit. So at t equals 0, right after the switch is closed, the capacitor is going to be empty, and the voltage is going to be full. I mean, the current is going to be as high as possible because there's no counter EMF from the capacitor. So the capacitor is just acting like a wire at the beginning. We have epsilon is driving a certain amount of current into the resistor. So at t equals 0, we have current is just going to be equal to epsilon over R. And we're going to know that charge is going to be equal to 0. And also voltage of the capacitor is therefore equal to 0. At t equals some other t equals x, at some point, well, we don't know. That's what we're trying to solve for. At t equals infinity, so after a very long time, the circuit's going to have settled. And the capacitor is going to be full. The resistor is no longer going to have any current flowing through it, so there's going to be no voltage drop across the resistor. And we have to figure out the max charge. So we have I is going to be equal to 0. What's Q max going to be equal to? These are all max.
It's the capacitance. Something has to do with the capacitance.
So the voltage across the capacitor is just going to be equal to negative
It's
voltage
V over
of,
the voltage of the.
EMF.
It's epsilon over C, right? Capacitance.
It's epsilon times C.
Okay, times whatever.
Yeah.
Correct. Who came up with
Yeah.
this?
Voltage is equal to this. Great.
Well, voltage is equal to Q over. Oh,
Wait, so
okay.
that
Why
means
am I
that-
stupid?
Does that mean that VR is equal to 0? In t equals infinity?
Why would that matter?
I don't know.
Sure. Wait. V what? What V? The V of the VR. Oh yeah. I think it's in time zone. Yeah.
I gotta go, Miles.
Okay.
Rah rah.
I'll watch the lecture.
Yeah. Okay.
Take notes.
But no. Okay.
See you later, chicken. See you later.
Bye bye.
Bye, guys. Bye-bye.
Bye bye.
Okay. And so the takeaway here. I'll erase all this. The takeaway is that Qmax is equal to CE.
Epsilon.
Yeah, sorry, C epsilon.
It's
Dude, it's so easy to just say, oh, it's got P. It's not a rho, it's a P, or it looks like an E, it's not epsilon. It's like second nature, almost. Okay. So, that means we can substitute that into here, into our equation here. Q max minus dq dt times RC minus Q equals 0. Cool. Next, we want to separate our equation. Can you pay attention?
Yeah. You want to separate the equation.
We want to separate the differential equations. So we have, if we just get this all on one side, we have Q max minus Q equals dq dt RC. Then we can multiply RC on both sides and then flip both sides. So So we're gonna have 1 over RC times Qmax minus Q is equal to dt dq. So we flip those sides, and we move dq over here. Oh, sorry, I did this wrong. RC is at the top. Actually, we can leave it on this side. dt over RC. Okay. Nice. So here's the fun part. Now we integrate it. Okay. What are the bounds of our integral going to be? They're going to be different for the two integrals because we have different variables.
From what, 0 to infinity? Because they're taking time.
We're trying to solve for it at a certain time x, not.
Oh, 0 to x, yeah.
Yeah. So for t, we're going to have 0 to x.
dx? Or dt?
X is just x. Yeah. For q,
That'd be
we're going to have from q initial.
to q final at q at x.
Not to
equals
q final,
x.
just to q.
Where t equals x.
Yeah.
Ah.
That's what the q is in this
Okay,
case,
yeah.
q t. It's important to note you can have an initial amount of charge in your capacitor, and this equation will still work, but you're gonna have a slightly different equation because you're gonna have qi in there. So we're gonna assume that there's possibly some initial charge in there. Sorry, I wrote q equals 0 on t equals 0, but it's not necessarily like that. Okay. Integrate. Nathan, I'm gonna give you the easy integral because you probably can't do the hard one. You haven't taken calculus 3 at all or anything. So, what's the integral of the right side?
What's 1 over RC times is 0 t over RC.
T over RC. Or x over RC.
Yeah, x over RC.
I like to just use the t variable.
Okay.
It's easier. Okay. Right side. Where should you get the fun integral?
I don't know. I haven't taken Calc 3.
You don't need calc 3.
You don't need Calc 3?
No.
Oh, then it's probably. Isn't it ln q? No.
Yeah.
Yeah.
Keep going.
ln.
Negative ln.
Yeah, negative ln, and then.
Let's just do this thing. QI, QF.
Oh wait.
The absolute value though.
Yeah.
I don't think we need it.
I don't
Or,
think
okay,
it
well
is.
it's negative ln of the absolute value of Qmax minus Q, right?
Wait.
So that's what the actual integral would be. Assuming Qmax is a constant, which it is.
I don't think the absolute value matters in this equation. Luckily,
Well, I mean,
it
you can
somehow-
prove that it doesn't matter by saying
Right.
Qmax is always greater than Q, which is obvious.
Not necessarily. You could be uncharging the capacitor. If it had some EMF and it was at a lower.
Well, Qmax is always going to be greater than Q, though, right? The max,
No.
you can't charge more
Not
than
necessarily. You had a charged capacitor and you put it into a short circuit.
Okay,
Your
yes.
EMF was less than it.
But
But
this,
okay.
this
So it ends up being canceled out by because you divide it. So don't worry about the absolute value.
negative ln of Qmax minus Q.
Qmax minus Q. Okay. So then we can expand this. So ln of negative ln of Qmax minus Q minus plus ln of, or this is QF, Qmax minus QI. And we can change this into a division.
Oh damn, son.
Okay. ln rules.
I love
We can divide
the
it.
rules.
Oh, yeah, yeah. I always forget those.
Okay. I might run out of whiteboard space here, Loki. So now we put, I think we want this to be the other way around. We want F on the top and I on the bottom. So that means we put a negative sign over here.
Oh yeah, you're right.
So now we put U to both sides. Qmax minus Qf over Qmax minus Qi equals e to the negative t over Rc. The next step here is to 1 minus both sides. And it's not really apparent why, but it's actually because it will make this numerator a lot better. So if we do 1 minus on this side, if we do 1 minus on this side, we just put the denominator minus the numerator. Qmax minus Qi. Here we have Qmax minus Qi minus Qmax plus Qf. Cancel out the Qmax is on the top. And now we have Qf minus Qi over Qmax minus Qi equals this thing. Okay. Yeah, this is such a mess. Okay, we're gonna move this over here.
Jeez.
Okay. So finally we have, if we just want to solve for, we want to solve for Qf. Oh, sorry, I've been using F this whole time. This is just Q. Oops. I mean, it's the same thing.
Q1 t
Q,
equals
Q and
x.
T equals X, yeah. Okay. So solving for Q now, we have Q equals 1 minus e to the negative t over Rc times
Qmax minus Qi.
Qmax minus Qi,
And then plus Qi.
plus Qi. Great. This is our
Alright,
equation.
that's
That's our time constant equation. One of them.
Yay!
It's not completely done yet, but this works. So yeah, that's what the graph of Q looks like. But
Excuse
there's more we can do with it. So the general time constant equation, now that you've done one of these derivations, a lot of them look really similar. So you can use the general formula for it, and that's change equals change attempt times 1 minus e to the negative t over tau. It's like the change goal or change attempt here. That's like from where you are, Q initial to Q final. That big difference. And then change is the actual amount of change that has happened. The tau is called the time constant. The time constant is the amount of time to get 63.2% of the way there.
To charging the capacitor, you mean?
To charging the capacitor,
To
yeah.
the max capacity. To the max
To the
charge.
max charge. 63.2% is 1 minus e to the negative 1. Sorry.
Oh, okay.
Yeah.
That's equal to 0.62?
63.0.
0.622, yeah.
Yeah.
In this case, what is tau?
RC.
RC. That's why it's called an RC circuit, because the time constant is RC. There's another time constant derivation in electricity and magnetism with magnetic inductors, and those are called LR circuits. The time constant is actually L over R, but whatever.
Kind of like digital circuits and analog circuits.
What do you mean? You don't like them?
Oh, I know them.
You know them?
That's other types of circuits.
Digital and analog, sure. Okay.
I'm like,
Yeah, man.
So yeah, just remember how to do this entire derivation, and you're good.
Really?
Yeah.
Okay, what worked?
Actually, not too bad.
Right.
Totally right.
Okay, I'm gonna erase this though. A couple more things.
You need this entire derivation.
Yeah, you need to know how to do the entire thing. Yeah.
You're right.
If you want to get voltage of the capacitor, we have to do the entire derivation again. No, just kidding. We can use the stupid change equals change goal thing, and that's good enough. And so V is equal to, so we have change equals change goal times 1 minus e to the negative t over tau. And that just means we can put like value and then initial over here. This change is equal to value minus initial, or final minus initial. So we just put initial over here. So V is just going to be equal to the change goal of V. So we have V max minus VI times 1 minus e to the negative t over RC. And yeah, plus VI. It's the same thing. Or it's also just equal to Q times C. Multiply the capacitance by the charge, just like you always have been able to do with the capacitor. Yeah. And then I is a little bit different. It's the derivative of this equation, or the derivative of the charge equation. So I equals dq dt. So the derivative of Qmax minus Qi 1 minus e to the negative t over tau over with respect to t. So I want to take the derivative of this.
With respect to t?
Yeah.
No.
Okay, just foil it, bro.
This is just a constant.
What, it's negative,
Alright.
yeah, you can take out the 1. So it's negative t over r.
Oh yeah, don't foil it, bro.
It's gonna,
Oh,
I don't even remember how to take the, like e to the power of x is e to the power of x. It's like e to the power of x, sorry,
e to the power of x.
negative e to the power of negative t over r
Oh,
over log of q max minus qy or something like that.
bro.
I don't remember.
RC. So we have this, and then
The
our
derivative.
chain rule for e's we have negative 1 over RC.
So yeah,
So just make this positive divided by RC. Great.
Oh, that's it?
Yeah, that's it.
Okay.
But isn't e negative or something? Or negative q max over positive qy plus qy? Because e's negative. Oh no, the chain rule. Yeah, okay, I'm stupid.
Okay. So this is I. I is also a time constant equation. It just had like weird.
Where'd the dt go?
Yeah, where did the C go? If
The C.
TQ
There's no c.
I don't know, but like ADQ equals QC.
Huh?
Oh, I'm stupid. This volt. My fault. My fault.
Yeah, so you can use, I think you can just use also like I max and I initial, but the thing is I is never going to be like have a maximum of it's never gonna have a maximum of something that's not zero, because current is the derivative of the change in Q.
So,
Yeah, and then I already showed you guys what the graph looks like.
Okay.
alright, that's all. For
Wow,
RC
you
circuits.
think I should get this? That's the Sheen S and Sean's. That's not essential. It's an S and Sean.